This is Richard Courtney, and I'll let him introduce himself.
Thank you.
I'm sorry.
This is very. If you could find me Sven's Mark's thingies, because they are there. Right, friends. As not Sven, Jaworowski's. Hey, that was good, wasn't it? I mean, really, those two present. Now that's climatology, a practical science that has real application in the real world of benefit to you and me. And thank you, gentlemen. That it was worth coming all the way across the Atlantic to hear you two. I'm a genuine. Thank you. And you must be very disappointed not to be having Zbigniew Jaworowski here, as I am. And I need to tell you why he's not here and why he thinks, and it's been agreed by the Heartland Institute, that I'm someone who might be able to present something of what he's done. He's had a heart attack past few days. I learned of this on Saturday. He considers that I'm a reasonable person to present his work, which I had not seen until I was just before I was leaving to catch the plane on Saturday, and I hadn't seen his illustrations until last night, so this is very much off the cuff. But why is it so worthwhile to hear Zbigniew's information, even though he can't be here? The answer to that is quite simple. We've all heard repeatedly there's very little data that can be trusted. But there is some data that is trusted as an article of gospel faith by some people, and that is the ice core data showing the history of atmospheric carbon dioxide concentration. Zbigniew probably knows more about ice cores than anybody else. He's an expert on radiological protection. Undoubtedly the world's foremost expert on radiological protection. When the Chernobyl disaster occurred, the United Nations put him in charge of finding out what had happened, who was going to get hurt, what the long-term effects would be. Remember, this is an academic from the then Warsaw Pact countries. Not someone that one would have expected the West to think was a first choice. Nobody objected to Jaworowski doing this job. Class of his own. And when you talk about ice cores, Tim's work on his sediment core, wow. But he's shown you core analyses are not that simple, they're straightforward. Jaworowski, he's really the granddad of this sort of stuff. He mounted 10 expeditions to glaciers and polar regions to collect ice cores, and defined methods for extracting ice cores, for sampling ice cores, for analyzing ice cores. So if anybody knows about ice cores, it's Zeb. And all these people who tell you they know about ice cores, well, some of them weren't born when he was doing this stuff, first of all. And that's when he came to find me. You see, I'm a materials scientist, and I'm really pleased that Fred Goldberg's in the room, because I usually turn up at these climate conferences and I'm the only materials scientist present, but I got Fred as it told me hand. Jaworowski wanted to find out what ice really does, what ice really is, because water's funny stuff, you know. It doesn't behave the way you think it does in almost any of its forms, and as ice, it's really weird. And at the time, I was working at the UK's coal research establishment, which was shut down in the 1990s for political reasons, but at the time we're talking about was one of the world's leading energy research establishments. And coming from the nuclear base, in those days, coal and nuclear were at one another's throat. And it was thought going there was really independent, you see. So I was asked to work with him, and that's why it's thought that I know a little about what he does, because I worked with him for some time. And what he argues is the ice cores not merely don't tell you paleo data on CO2, they're worse than that. They give you misleading data on paleo data for CO2. And wrong data is actually worse than no data. If we can slip on a bit, can we just, yeah, we'll start with that. You see, there are a lot of assumptions involved. And the whole global warming, anthropogenic global warming thing is based on these assumptions. The assumption, and it actually is an assumption, that there was a stable pre-industrial level of atmospheric carbon dioxide that was around 290 ppmv. And the assumption is justified on the basis that if you measure air trapped in bubbles in the ice, that's what you get. Well, not strictly, because if you look at some of Indemul's papers, earlier papers had much higher levels than that, but it was decided that anything that was above 290 had to be a biological artifact and therefore was deleted from the same series in some later papers. But ignoring that, assuming that all those high values were biological artifacts, it's all at 290. And this stuff started coming out in the 80s and 90s, all this 290 stuff. And Jaworowski said, hang on a minute. I've been analysing this stuff for decades, and it don't mean that. Let's move on to another one. Oh, this is a lovely one. Because, you see, Callender, who thought up this 290 business, he also had info on CO2, and this was all taken from the air. In fact, there's a guy called Ernst Beck who's done a load of analysis of literally thousands of these old studies of atmospheric CO2, and he's come to the conclusion that he can actually draw, related to historic CO2, historic temperatures, relationships of atmospheric CO2, and some of them are way above what we got now. But Callender decided that you see the ones with the circles round? Those were the ones he used to calibrate for Mauna Loa and were later used to calibrate against the ice cores. You see all the other dots? Well, they had to be wrong because they were I. Can we move on to another one? Oh, this is a mention of Beck's 19th century CO2 concentration as an average of all the direct measurements in the air, not stuff stored anywhere, but made at the time in the air by real good scientists. Some of them Nobel Prize winners for chemistry. They end up at 335. Yeah, next one. This is Beck's relationship again. Let's keep going. Oh, this is interesting. You see, the ice cores aren't the only stuff which goes back. There's the stomata data. Stomata are holes, pores, in the leaves of plants. And if you change the CO2 in the atmosphere, the plants change the size of their holes. This is a direct measure of CO2 in the atmosphere, and you can calibrate it. You change the CO2, the holes change size, just like you change the temperature and the size of the mercury in a tube of glass changes size. You read the mercury difference off and you say, well, that means the temperature moved that much. You see the holes change that much, you say that. Got it? Have a look. Data speaks for itself. The ice core data, not a wobble. Look at that, you're stable 296. But the stomata data, you see, you can find leaves They fall in peat bogs and things like that. And because it's anaerobic, as we've just heard so eloquently from Tim, you can find things which just don't rot effectively. So you dig the leaves out, you stick them under the microscope, you can measure it. Well, that's what the CO2... But you don't believe the stomata data because we all know there was a 290 ppmv stable pre-industrial. Well, we don't know it, don't we? We all know it. So the stomata data got to be wrong, haven't they? Because, keep going. It is absolutely essential that for the CO2 trapped in the ice to be real measure, the system of the ice bubble is closed. It's got to be a solid locked-in thing. It's like, take one of those bottles, you put some air in it, you put the lid on, nothing's got to get in, nothing's got to get out, because if it did, you'd have a wrong result, wouldn't it? Well, it's just the same with a bubble. And that isn't so. And it isn't so for a variety of reasons. The first reason is how the ice forms. The ice forms because snow, precipitation, falls down, and it sort of builds up, you know? And then it sort of compresses down under time, and it turns into ice. That's how the ice, sort of, right? You call it firn when it's not formed solid. Now, we material scientists don't call it firn. We call it open porosity, but, you know, we'll leave it to these climatologists to think out their own language, because they do that a lot. And then the ice solidifies. Well, that process alone is a problem, because think about it. One thing you know about gases in high concentration is they move off to places where it's lower concentration, don't they? And since it takes, according to the IPCC, 83 years for the ice to seal, that means they've got 83 years to move. Well, that's equivalent to a simple top-hat filter. It's an 83-year moving average. It's effectively doing an 83-year moving average on all the annual data. Well, you think about how long we've been measuring CO2 at Mauna Loa. It's only since 1958. You do an 83-year moving average on that and see how many peaks and troughs you get in it. Have a look at the stomata data. We sort of remember the stomata data. No wonder it's smooth. That alone. Move on. Let's see what we can get. One more, because I'm using up too much time. Right. Early studies on gases and ice showed ice is not a closed system. It's in proper matrix for construction of an ancient atmosphere. Years spent on improving the analytical techniques did not change the polar ice into a right matrix. The ice is not solid. There's a simple problem with ice. It's always wet. I mean, it's always wet. There's a guy called Faraday, Michael Faraday. You might have heard something about him. He did some stuff with electricity. He also did, among many other things, a beautiful lecture at the Royal Institution, all about ice being wet, at temperatures down to -73 Celsius. It always is. Do you know why ice skaters slide? Do you know? Anybody know? So, Fred?
It's a wet surface.
It's always a wet surface, isn't it? It's always wet. When you say ice freezes not at the surface, it don't. I told you, water's funny stuff. Until very recently, we didn't know why it's always wet. But now, with something called nuclear magnetic resonance imaging, NMRI, we can actually work out why. It's to do with the fact that there's no bonds located at the surface, and there's a few bonds and they vibrate one against the other, with the net result that the molecules along the surfaces just act like water, because they are water. So long as you got a bubble, you got water. And if you got water, you got solution. And do you know the gases dissolve different? You will always get wrong results. Entrapment of air is a mechanical process. No liquid water occurs. These are all wrong. The air is well mixed with the atmosphere down to the beginning of the... No, it don't. Age of gas is much younger than the ice in which the... Much younger, 83 years younger, according to the IPCC. The IPCC says all the gas in the bubbles moves up through the ice, 83 years. Well, it has to do that, otherwise it doesn't match with the Mauna Loa data. Frankly, I can't say it was that because there's ladies present. It's not sensible. This is the best I can put it. And Jaworowski saw all this from the start. Jaworowski says, experimentally, liquid water is ubiquitous in polar ice and snow. There are 20 physical-chemical processes operating the ice caps and ice cores that contribute to the fractionation of gases in the air bubbles. There's a ubiquitous dense network of thin horizontal ice layers in firn that presents a barrier for migration of atmospheric air deep into the firn. All in all, the ice cores are not merely wrong, they're misleading. They should be rejected. Using them to establish policies for the entire world is nonsense, dangerous nonsense. Jaworowski has done much more, but I hope I've given you some insight into why his work is important. And if I have, I hope you will look into his work some more for yourselves. Because if you understand that, you'll understand the entire global warming idea is just daft. Thank you.